Welcome back, everyone. I am very pleased to see how the last article, The Unreasonable Effectiveness of Mathematics in the Natural Sciences by 𝐒𝐮𝐻𝐬, started a big conversation about the topic. And this paper came up in several comments, and of course, you find it naturally when you're discussing math and science and how they are related and to what extent they are the same or not the same. And this is the paper mentioned in those comments several times, The Reasonable Ineffectiveness of Mathematics by Derek Abbott. This was a joy to read and certainly helped to probe my brain into new points of view, which the paper definitely succeeded in. And I could definitely see why, because this author presents some pretty good arguments, in my opinion, following Eugene's paper. Of course, this paper was 20 years post Eugene's paper, so I think they had better structures to argue on that from that point of view then. And within this paper, the opening paragraph and passage tells us about two perspectives that we need to pay attention to. Mainly the school of thought that reflecting from Plato, hence this nice picture here, which is definitely a foreshadow of Plato crossed out on a background of mathematics. Where the Plato's school of thought is that mathematics has its own existence versus the opposing viewpoints of that mathematical forms are objects of our human imagination and we make them up as we go along, tailoring them to describe reality. So really we have two perspectives that are in the holistic viewpoint of this paper that need to be brought up. So let me bring over a sticky note that describes these things. Oops. All right, so for the Platonist viewpoint, this posits that such abstract entities have an independent objective existence in and of themselves. Math is its own thing, some call it science in and of itself, things like that. Versus the non-Platonist viewpoint, which rejects the idea of abstract objects, such as numbers, mathematical truths, and other forms, and that they don't exist independently of human thought. So keep these two concepts in mind as we drudge through this paper because they become very obvious, and we need to keep these definitions in mind to understand the writing that was given to us and how things are framed for the arguments themselves. And so later in this intro passage, he points out how two other topics that come up, which is rarefied and anthropocentric perspectives, come into account. So let me get those definitions on the board too before we move forward. Here, rarefied is treated or represented as a concrete, tangible object made real or concrete in perception or practice, and anthropocentric is centering or emphasizing human beings and their importance, often to the exclusion or detriment of other species and the environment. So I think it's, after reading this a couple times, it's very clear that these two words work into how the argument structures themselves. And we will definitely come back to that, because if we're saying that we're a non-Platonist viewpoint and that we're using anthropocentric arguments or framework to run from, of course we're going to center the human being's experience over all else. And thus, if it is a thing of the human imagination, we need to be able to separate that from, is that just what we want for the humans to succeed, or is that what we need for actually describing reality? So very cool there, and hence rarefied comes in there to see what is actuality versus what we made up. So let's go ahead and dive in more into this article because it is fun. The opening definitely gives us a nice thing to have with the idea of what framework we're going to peruse in this paper. So let's dive into the opening segment here, which is mathematicians, physicists, and engineers. And in this section, what he talks about a lot of is how different scientists or different people within these three sectors view mathematics. And we can best summarize this as most mathematicians are Platonists, believing in the independent existence of mathematical entities. Really no shocker there. Physicists often appear Platonist publicly, but are usually non-Platonist privately. Okay, and I guess we could see that with some of these emerging theories later, why that is the case. And then later he talks about how engineers are openly non-Platonist, recognizing the artificiality and limitations of their models. Where, they talk about things like circles and delta functions are practical tools rather than real entities. And, he goes on to say how real circles, these ideal circles, are not really seen in nature, so to speak, but they're great approximations for what we see in nature. And then Abbott also talks about how engineers will manipulate their models to fit practical needs, often working with abstract spaces to achieve physical outcomes. And one of those things that came to my mind was transforms, things of that nature, getting a function domain into a transform domain, doing the math there, and then transforming it back. That could be a way of taking an abstract viewpoint on what isn't necessarily reality. So that's a great opening segment there, and really sets the stage for what he's trying to do. Of course, he gives good input, and you could read the annotations there, and I'll post the links below. But that was a pretty good opening for what he then gets into usually. Then he gets into after. Oh, sorry, I'm rambling. So then he goes into section 2, which is, do fractals have their own existence? And this one was cool for me because this really puts into perspective what we as humans deem as beauty and what someone else might deem as beauty. To summarize the section, we see that Roger Penrose argues that fractal patterns are evidence of mathematical entities existing independently on a Platonic plane. Okay, maybe that could be an argument, but then of course we have objections directly after the statement by Roger Penrose. One objection is that the perspective of fractals as beautiful is anthropocentric, and of course in different beings we might find different patterns appealing, which I think that makes plenty of sense as an argument, because your idea of beauty and my idea of beauty are probably different, although we're both humans. So imagine what different species might consider as beautiful. And then they reference aliens and things like that just to get out of our bias of the creatures here on Earth. And then another objection is that there are infinite possible equations, yet only a few result in appealing fractal patterns. So this is similar to selectively finding meaningful sequences in random digits. Of course, that definition of meaningful or beauty is an anthropocentric point of view because, again, a different species might not find that same thing. The beauty and complexity of fractals or games like chess and are human constructs and do not indicate a Platonic existence. And he finishes off this segment in the argument of that the axioms underpinning mathematical forms like fractals are themselves mental abstractions and not universally real. So we're having this very big push between Platonism and non-Platonism and what perspective is actually good for what we're trying to do. Which then leads us to part 3, the ineffectiveness of mathematics. And here, this is a very hefty chunk of the paper to which he posits Hamming's 4 propositions on the stuff and what's going on there. And it's very interesting to see how this should change your perspective on, is math actually effective or ineffective? So to start, we can summarize this opening dialogue before he gets to, not dialogue, but opening passage, before he gets to Hamming's first proposition as, the author argues that mathematics is useful mental abstraction, but its effectiveness might be overstated. Okay? And we see that particularly as electric engineering particularly as electric engineering approaches the nanoscale, where empirical models and simulations replace traditional analytic equations and analytic tools of mathematics. And then he continues on by stating that the complexity of modern devices and systems often necessitate numerical simulation over analytic calculations, highlighting the limitations of traditional mathematics in certain contexts. The perceived effectiveness of mathematical laws, like the inverse square law of gravitation, might be influenced It might be influenced by humans' perspectives and scales. And this idea of human scale is definitely something that comes up again. And I was not really thinking about that on first approach, and I'm glad he puts it in here. And mathematics is notably less successful in modeling adaptive systems like biological, economical, and social phenomena. So a bunch of great input there as to why we seem to like mathematics as successful when we only point out the successful mathematics in publications or theory, development, things like that. And yet we use a lot of numerical tools and stuff to help us on practical stuff like engineering applications. To which this leads him straight to Hamming's first proposition, where Hamming argues that our problem solving is influenced by our intellectual tools, and as new tools like big data and complex systems emerge, traditional mathematics plays a smaller role, with large-scale computing being used to identify patterns. And that concept will come up again later in the paper. B, Hamming's second proposition, where Hamming suggests that mathematics evolves to address specific problems, developing new tools as needed. While Platonists argue for the pre-existence of mathematical concepts, citing the prior development of 4D curved space before the application of general relativity, though this may be seen as a selective interpretation of coincidences. So, I could see how that could be a quick argue. As you see, we cherry pick successful coincidences, as I highlighted here in the text. And then let's move straight to part C, Hamming's third proposition, which is the apparent success of mathematics is partly due to focusing on problems it can effectively address, like linear systems. And we see that, linear systems and superposition, things of that nature, make those theories very successful, although the development of nonlinear systems has not been the same. And while more complex nonlinear systems highlight its limitations, and Gödel's theorem underscores inherent limits on what can be proven mathematically. So again, I could see why he's poking holes using Hamming's propositions, although Hamming made a paper in and of himself with these propositions in more detail, if that's something you're interested in. Now on to the fourth proposition by Hamming. Our intellectual abilities may have evolved to understand local reality effectively, which makes sense because we need to keep humans alive, so problem solving on a human scale in the local reality makes a lot of sense. Go back to the anthropocentric viewpoint that was mentioned in the opening paragraph or opening passage. So, and then later on in this part D, he says, or makes the point of suggesting we are naturally suited to analyze the world at a human scale, but struggle with reasoning about the very small and very large scales of the universe. That makes sense. We're not, we can't zoom in all the way to the Planck scale or zoom out all the way to the galactic scale with our eyes. So tools have to be developed and so on and so forth. And what I found interesting about Derek's approach here is he puts two more potential propositions in to aid this point about the ineffectiveness of math. And in part E, he goes on to state how physical laws and mathematical expressions are compressed representations suited to the human mind, idealizing reality by removing noise and the stochastic elements, and when we uncompress them to solve problems, they yield useful but not entirely accurate results due to inherent information loss. And that makes sense, because think about how we say, well, neglect air resistance in this very idealized model for falling balls in physics 1, things like that. It became very interesting to see how this was looked at in viewpoint of what actual reality is. And if you haven't been aware to what stochastic processes are or what stochastic probability is, things like that, stochastic is relating to or characterized by randomness, involving a random variable or process. So interesting that he's thrown that in now, because there is a lot of noise, And then then he goes on to talk about lossy compression, things of that nature, which will lead to information loss and information leakage. Following this, he adds on another postulate, which is the 6th point of this big paragraph and central part of the paper. And to which he says, for the Darwinian struggle for survival idea, Wigner's sense of magic is the success of mathematical models can be explained by the pre-selection of successful models through a Darwinian process where only models that have survived experimental validation are published, creating the illusion of automatic success amidst the many failed attempts. And, I think as a different point of view or a tangent to this, I wish we would publish more, quote, failed experiments or failed models. That way we can learn from the failures and not only highlight the one out of however many that do pertain any, quote, meaningful change to what we know now. I think that would save a lot of time and money depending on where and how it's modeled and published, but that could be just another idealism in and of itself. So, to challenge these concepts like anthropocentric views, verified, Platonist, and all this other stuff, Derek puts another section in here. Well, what about the aliens? And once you read these things, it kind of changes the perspective on what we have, or at least it did for me. And we could summarize this section pretty quickly by stating things like, mathematical Platonists argue that mathematical entities like the number pi have a Platonic existence, since any intelligent alien civilization would likely discover and use them. Okay, and that's what we see here highlighted: simplicity of geometric objects, ideal circles, so on and so forth. Yet, the universality of such mathematical concepts is questioned, suggesting that not all aliens may find interest in or use complex mathematical objects like the Mandelbrot set or the delta functions. Why would they? Would they ever want to? Things like that. Especially because, I don't know if they say it in this section. Let me scroll down. Yep, they do. Let me finish these bullet points real quick, and then we'll talk more about a couple of things that were in this passage in and of themselves. So the next summary point here is that aliens might approach physics and engineering differently, possibly without the need for certain idealizations or Occam's razor, and might model all phenomena stochastically due to the inherent noise that we see in reality. So we can see the highlights there, idealization and Occam's razor, things like that. And the final point that I really took away from this is that a super intelligent alien race might not rely on analytical mathematical reasoning, but instead perform vast numerical simulations mentally, indicating that human mathematics is a tool adapted to our cognitive limitations. And if we run numerical simulations and empirical model simulations, things like that, to find patterns that we see in big data, what's to say that these aliens can't do it in their head and all these other things that we look for as a kind of, hand-wavy science or hand-wavy math, but lead to more accuracy in reality because of the inherent noise. That was a really kind of changing perspective moment on this paper, and that makes a lot of sense if that's what we go to. And I'm thinking of things like numerical solutions for PDEs or FEA, finite element analysis, computational fluid dynamics, all these things for the higher complexity situations that we have. That can kind of be a good argument, in my opinion. And then one such thing that he mentions here is Occam's razor, and I think that it's worth putting a definition down for Occam's razor as well, and I will do that here soon. But be aware that Occam's razor is used as an argument criteria for humans. Basically, that the simplest of any hypothesis is probably, which the simplest meaning takes the fewest assumptions, is probably the right one. And that may not actually be true. That may just be due to the humans, going back to anthropocentric viewpoints. That may just be what humans need to deal with in order to further idealize a situation and remove, quote, inherent noise. Pretty fascinating. And now we get to an application of how math may actually break down in the form of counting in section 5, where he states, 1 banana, 2 banana, 3 banana, 4, things like that. And this one was fun to kind of have a mental thought experiment with. And it's summarized as, the passage reflects on the abstraction of integers for counting, highlighting the complexity underlying seemingly simple mathematical concepts. Okay? Because it discusses the challenges of defining boundaries between objects and reality, using the example of counting bananas, and suggests that our mathematical concepts might differ in a hypothetical environment. And we see here that there's an arbitrary decision with what minimum density of banana molecules before there is no banana. So, and this is kind of a prelude to what happens next. Based on the limitations of physical memory and the ultimate physical limit, such as gravitational collapse into a black hole, impose constraints on counting and challenge the absolute reality of the integer number line. Because if we have, for some large n, very large n, we need memory to count them and store that, and then we say, well, if n is so large that it creates a black hole, to what point of these collapse there do we lose the molecules per banana arbitrary decision, and we just don't have any bananas? So as we get infinitely big and as we zoom in infinitely, eventually we lose what it means to be a banana and all those other things to counting. The limitations to storage on counting get lost too. So even in these hypothetical boundary cases, it's still an abstract thought that he's arguing for, and thus the counting itself is abstract and not a thing in and of itself. And so finally, this concludes with the argument extends to real numbers, with Davies suggesting that they are also fictional due to the universe's capacity constraints, illustrating the intricate relationship between mathematical abstraction and physical reality, as you can see here in the last part of this first column. So pretty interesting information. And I don't know if this is true, but the most that the universe can store is 10 to the 122 bits of information. Can somebody verify that? Because I'm not sure if that is true, but would be cool to find out. And then in section 6 here, which I really wish he would have put this earlier when he was, talking about the two viewpoints to have regarding this topic, which is strong non-platonist viewpoints or non-strong Platonism. And we see in the yellow here what it means to be Platonist, and then here in the pink what it means to be non-Platonist. I just wish this would have been talked about before. That way we can have these working definitions going into all of it. But nonetheless, summarize what we see here is that these two concepts are summarized in this little passage, where the strong non-Platonist challenges the interpretive value of physics, suggesting that human-centric interpretations are illusionary and incomplete, as exemplified by the analogy of 3D particles passing through a 2D universe, i.e. we only have so much information to take, but we are lacking in omnipotence. And, omnipotence was another definition I feel was worth putting together, and it states the state of having unlimited power or authority. Pretty interesting there. Another concept that they had here with regards to engineers is that the engineers are in control of their own universe, and they use the word fiat to describe the changes that they can make to the model to kind of fudge things and make it work. And fiat was another level of authority argument to have in breaking things up. So pretty cool. I was not expecting that to happen here, but, furthering in this passage here, we see that humans are limited to perceiving the world on human scales, and while instruments extend our reach, we are far from omnipotent, which is true. Some models, let me get my thoughts together. Some models in physics are knowingly built with imaginary interpretive value for convenience, such as semiconductor holes used as mental constructs to engineering devices. Fair enough. N-type, P-type, and we see how the holes move through, and we can get data from that. But he also says here a cool example of the sun. If we talk about thermal equilibrium, if we talk on a galactic scale in the sun, one thermal fluctuation might heat the planet that we're on, and on a human scale, but in the totality of things, that might just be thermal equilibrium on the galactic scale. So scaling is definitely a thing here. Very, very interesting. And then John von Neumann's perspective underscores the pragmatic nature of scientific models, emphasizing their utility in describing the observed phenomena rather than attempting to provide ultimate explanation or interpretations. And that's this block here, a nice quote by John von Neumann. Very smart guy there. And then after that, we bring into ourselves section, 7, immutability. And this is where I have to bring my last sticky note of definitions. We talked about Occam's razor, which is a philosophical principle stating that among competing hypotheses, the one with the fewest assumptions should be selected. Then we get to immutable, which is the unchanging over time or unable to change. And he leaves this with the famous words of any text that anybody's read in science or engineering. I will leave this as an exercise for the reader. So with this, I would love to hear your comments about what physical laws have this trait of immutability. And then we could have a discussion about that because I think it'll be a fun talking point. So please do comment on that. Oops. That's down. Sorry, guys. All right. So with that, the human brain demands compression of nature. Occam's razor is our mental tool for sifting out compact representations, is what he ends that passage with. Pretty cool. All right. And then on to one of the last parts of this before conclusion is a personal story, to which I will just read through my bullet points here to save time. We have here that the author recounts childhood experiences with counting cardboard boxes, noting the loss of magic when realizing inconsistencies, serving as an early lesson in experimental repeatability and demystification of science. And despite enjoying mathematics in school, the author suggests with the concepts like infinity, negative numbers, and raising numbers to powers of zero, questioning the artificiality of mathematical concepts and tools. And the author also found that mathematical proofs were intriguing, but was troubled by their ad hoc nature and philosophical uncertainties regarding the correctness, particularly for lengthy proofs like Fermat's last theorem. And so and that makes sense because it's kind of ad hoc in some representations of proofs because you have like direct proof, proof by contradiction, proof by contrapositive, induction, and so on and so forth. So it is kind of a handcrafting in that perspective too. And so, this is basically the passage that emphasizes the author's journey towards non-platonist viewpoints in mathematics, highlighting the subjective nature of mathematical postulates and so on and so forth, and the absence of divine ordination in mathematical concepts. And that brings us straight to section 9, why not just shut up and calculate? Well, the author suggests that understanding the nature of mathematics grants greater intellectual freedom, enabling proactive manipulation and application of mathematical concepts, negatives, imaginary numbers, and so on and so forth. There's criticisms of lack of uniformity in mathematics and tools, such as the Cartesian plane and the Argand plane, or complex plane, which are isomorphic, so why not just use the two? And then this goes on to a fun little segue into Clifford's geometric algebra, which joins together the likes of dot product, cross product, and tensors all into a multi-vector. And it was weird how vectors can multiply but can't divide. He brings up a lot of good, interesting points in this, and the freedoms there and the freedoms thereof whenever you let go of a perspective. And despite its historic sidelining, there's an emerging interest in this Clifford algebra in fields like physics, engineering, and computer science due to its simplicity and power. So just because something's always been used doesn't mean that that's the best thing to use. And then finally, we get to our conclusion. And to which he likens science to modern alchemy, generating wealth through understanding and creating valuable products from basic components. But it's noted for sometimes replacing old misconceptions with new ones. And mathematical Platonist, or Platonism, is criticized as a form of reductionism that breaks holistic concepts into imaginary dualisms with the suggestion that progress could be accelerated by dispelling this philosophical notion. Mathematics is described as a human invention for describing patterns and regularities in the universe, providing a sense of order even if the reality of these regularities is somewhat flexible. And with that, I will hopefully get another wonderful paper suggestion out of this video. But please keep learning, please comment, and above all else, stay curious.